Welcome to part 2 of Let's Build a Quant Trading Strategy. In this video, we're going to be focusing on the strategy development. In the previous video, we looked at the model, and the model was responsible for taking an input and making a prediction, which we denoted here as the signal. And now in this part, we're going to be focusing on the strategy. And the strategy is going to take our model's prediction and convert this into orders. And we'll look at the details of the strategy because there's a few key decisions that we need to make. And then the third part will be when we execute the orders and we actually code it all together. So there are two types of strategies. The first one is making strategies, which is where they provide liquidity, and they provide liquidity by adding limit orders. And the second is taker strats, which is where you take away liquidity, and this is done with market orders. So they take away the specifically off the order book. And we're going to be focusing on we're going to be making a basic taker strategy using our model. Now, I've got another video called Introduction to Quantitative Trading that goes way deeper into taker and maker strategies. So if you want the full breakdown, definitely watch that one, and I provide a link below. And so for our video, there are a few key questions that we need to ask. So let's just write them down. So the key questions that we're going to ask in this video for our taking strategy. One is, what's our entry and exit signal? The second, is going to be our trade sizing. What's the size of our trades? Because this can directly influence the profit and loss of our strategy. And then the third question is leverage. And leverage is essentially you're borrowing money, and this can increase your profits dramatically. But it also, by increasing leverage, you also have the risk of liquidation, where all your position is liquidated and you lose everything. So these are some of the three key questions we're going to ask and going to explore. And the key goal really is that we want to create a strategy that maximizes profits from the model's edge. So in the previous video, we built a model with a statistical edge, and we minimized the risk by looking for a model that has a high Sharpe value. Don't worry if you don't know what a Sharpe value is. That's also in the introduction video as well. So the first thing we need to do is to actually import our libraries, which I'm going to do now. And we're going to select my environment. Let this run. And so before, the first action is to load our model from the previous video. And also, I just should point out that I changed the model from the previous video. So it's not predicting 8 hours into the future now, it's predicting 12 hours into the future. And the reason why was to increase this time horizon is because the fees ate too much into the profit. So it was much feasible if I increased the hours, the time horizon. And we'll also increase the model's features because it was just using one feature. And now it's using 3 features, but we'll look into this in more detail. So the first thing we need to do is to import our models. And by the way, this video, even if you haven't watched the first part, I've made it as accessible as possible. So if you haven't watched part 1, don't worry, because I still believe you can follow through this without watching the first part, but I still recommend to watch the first part. So import models, and we're going to create our model. So in the models, we're going to create our linear model, which is what we created last time. But this time we've got 3 features. This is going to instantiate it. And now what we want to do is load the parameters. So what we're going to do is load state dictionary, torch, load, model weights. And a really key parameter is this weights only equals true, because this just ensures it doesn't run any arbitrary code, because it potentially could run, someone could have say some malicious code in here, and this just really is a good security flag here that you select weights equals weights only is true. And we also want to set it to evaluation mode. So this just stops it doing redundant calculations that's only needed for training. Since we've already trained the model, we don't need to, like for example, run gradients, so it won't run these. And there's some layers, but for example, like what's called like a dropout layer. We don't need this for testing our model. So this just makes it more efficient for testing. So that's our model. And so now I'm going to just run this. So you see here, this is our model represented in PyTorch. The in features is 3, and it's just the output is just 1, and it has a bias. But we're going to have a look at the model parameters and or give you an explanation of them. So that's what we're going to do next. So we are going to, because it would be incredibly boring video if I just show you the code how to print out the parameter. So I just wrap this in my, I've got a function that does it for me. So, and then we're going to run it. And you can see here, there's 4 parameters, 3 weights, and a bias. And you can so this is an autoregressive model. So we're looking at the previous log returns to predict the future log return, and it's a mean reversion model mainly because of the first lag and the second lag are negative. So it flips the prediction the other way. So for example, if it went down, that would be a negative log return. So it would likely to predict it's going up. But we'll look into this. I'll give a more intuitive example to demonstrate mean reversion. And so let's just go over what is mean reversion. So I'm going to start with a series. I'm just going to, I'll actually just copy and paste this, it'd be easier. So we've got a mean reversion log return time series. So, and you can see it's oscillating between negative and positive. And so what we'll do now is we'll plot it, because then it will make more sense. So now we plot it. Okay, so this is what a mean reversion looks like. So it's log returns. So, and it's going from negative to positive. This is a toy example, but the emphasis is like it's oscillating between positive and negative log returns. And you can see here the orange line is the central tendency. So this is the average, and you can see it's hovering around this value. So this is what the model is modeling, this mean reversion dynamics. So now we have a visual understanding of mean reversion. I just want to show like the interpretability of linear models. So, and we're going to do it with like a toy example. you're going to look at the for a linear model. And so what we're going to do is just define a very basic model. And we're going to say set the weight and the bias to be, I'm just going to copy these, actually it'll be easier. So for example, if the current log return is negative, we can easily interpret that this is a mean reversion model because the weight is negative, so we know that it's going to flip the sign and it's going to predict in the opposite direction. And this is what the beauty of linear models is, that they're very simple and they're very interpretable, whereas we're going to look at neural networks and say that they're not explainable. And I'm just going to show you a few other examples, right? So now if it's a linear model and it was a positive, like the current log return is positive, then it'll be predicting that the next time interval that it will be a negative log return. And I just want to show the influence of the bias here. So for example, if it was a very small price movement, so let's just say it was 0.02, that it doesn't flip the sign of the log return here. It still remain positive, and this is the influence of the bias here. And just to make it even more clear, so for example, if we set this to 0, the prediction will just be the bias, which you see here. Okay, so that's linear models. And now let's look at a neural network, just like a basic nonlinear network. So we look at interpretability, non-linear model. And what we're going to do, actually I think I will just copy and paste this. And I'll just explain the code here. So this just wraps the input into a tensor, but this is like the weights and this is the bias. So this part is like just a classic linear regression, but it goes through this what's called a non-linear activation function. And essentially what this is doing is mapping into either a bounded number between -1 and 1. And so for example, if I run this now, we can explain mathematically how it calculated this, but is it explainable? Like, can I give a good intuitive explanation why it chose this? It would be quite difficult to do. So this is the beauty of linear models, because they give you this explainability. Whereas with for example, imagine this was like billions of parameters. They're very powerful, but they don't give you that explainability. And especially as an introduction and just starting off, we want to use models that are explainable. And if we look at some other examples now, so for example, and we predicted, let's just see, a positive number. It's also positive, but I can't really explain why. But it may be that you believe that you don't need explainability. You're more interested in increasing the expected value, and neural networks could possibly do that. But they can increase your expected value, but at the expense of complexity. And just as this is an introduction, we're going to start with a linear model because they give good generalization and they have the less complexity. So now we're actually just giving you an explanation of the model that we created. Now we're going to actually go into the nuts and the bolts. We're going to go into strategy development now. And the first thing we need to do is to load the time series. And I had lots of feedback saying people had problems downloading the data because it was like over 20 gigabytes of data. And so just to save you time and headaches, that I've made it convenient for you to download. So what I've done is I've just saved the time series rather than having to aggregate it yourself. So that's what we're going to do now. So, and it just makes your life a lot easier. So we just need to specify the symbol, which we denote as this, and then the time interval. And we're going to load it now by doing this. We're going to do read CSV file. Time interval. Open, high, low, close, CSV. And we're going to we want to pass the dates as we're loading it. So we're going to set this to true. And we're just going to make sure that it's sorted, because for a time series, it's important to have what's called temporal order, which is essentially your dates are in ascending order. So this is what we're going to do now. Okay, so now we've loaded our time series. And what we want to do now is to add, which I'm going to say here, is add the target. And the target is a machine learning lingo for saying what we're trying to predict. And we're going to add the features as well. And this is also machine learning lingo to say, like, what are inputs. And because we've already done this in the first part, that what we're just going to do is just to use my research module to add them in, because it's just boilerplate code. But if this is the first time you're watching this video, I really recommend to check out this from my GitHub and look at the code, because I think it's quite important to understand how to build features and what's the actual calculations. So we're going to pass these parameters in. And the max number of lags is 3. We need to say what our forecast horizon is. So our forecast horizon is going to equal 1. So essentially what in the time series, it's a 12-hour bar time series, because you can see every row represents 12 hours. So it's going to be predicting one time step ahead. So that's going to be predicting the future log return 12 hours ahead of time. So now we're just going to maybe just display this now, just to show you the lags have been added in. So this is what we're going to be predicting, the closed log return. And we're going to be doing that based on the previous log returns, and we denote them or suffix them by this lag. And this is just for, so we're going to be using these 3 lags to predict the closed log return. So now we've got the target and the features sorted. Now what we need to do is we're going to split the data, because when we trained our data, we split it by time, the data by time. We used the oldest data to train the model, and now we're going to use the most recent to test the model. So it's imperative that we do this so it works with data it hasn't seen before. So the test size is 25%, and we're going to just take the test trades and just call them trades. And it's incredibly boring code to write, so I've got a function to do it. And a lot of my what's called boilerplate code, I create it in this module here called research, because there's lots of repetitive code that you need to repeat many times. And if rather than copy and paste, which is a really bad habit, it's much easier to put this into as a function and reuse this, because you have like multiple notebooks, and you don't want to be copy and pasting. For example, you want to change the logic, then you would have to change it in multiple different places. So it's really good practice that if you have any repetitive code, to put it into this like a module. So I've just got this module called research. So all my model development is all in one area. Oh, and then we want to call that trades plural. And I'm just going to display the trades just to show that it's split. So now we've got the base for our trades. So as you can see here, the start date is different here. So we're using the most recent data. So now that we split the data, we need to start developing our strategy. And so the first key decision is, I'm going to put here, strategy decision number 1 is our entry and exit signal. I'll make it put this. So what we need to decide is, when do we enter a trade and when do we exit out of a trade? And so there's 2 ways we can do this. Actually, so the first one is time-based. So we enter, so for example, we could enter a trade at Pacific time, and then 12 hours afterwards we can close the trade, and we do this on a fixed time interval. So this is what's called time-based. And there's another way, which I call predicate-based. So for example, your model makes a prediction, but you could say, like, if a certain condition is satisfied, then make the trade to either enter or to exit. So for example, if our model predicts like a very strong value, like above or below a certain threshold, then that could decide to be our entry signal. So, but we're going to focus purely on a time-based, because with the time-based, it complements our model, because we're modeling as a time series, like what the next future value. So we can make a trade at the beginning of the time interval, and then at the end of the time interval, we can create our exit trade. So, but let me just make it a bit more concrete. So essentially, each row represents what's called a round trip trade. We open a trade, let's say at the open, we make a trade at the open of the time interval, and then at the end of the time interval, we have another trade to close the position. Pardon me. We do exactly the same for the next time interval. So each interval, we make 2 trades. One to open the position at the start of the interval, and then another trade at the end of the time interval. So we know what's our entry and exit signal, that it's going to be time-based. So now let's add our model's predictions. So add model's predictions, because our strategy is going to be making decisions purely from the model's predictions. And we are going to, so I'm going to show you the code to do this. So the target is the close log return, and the features is, I'm just going to put it as this. Then it's going to be target lag 2. And now I've just got a function that's going to take care of it. So that we pass our trades in, we pass the model, we pass the features. And I'm going to show you what happens. So the model's prediction is denoted by y hat. So this is the prediction it makes. So for example here, it's predicting it's going up. And an example where it's predicting it's going down is here. And when we make a prediction, if we're making a bet, if it's going down, it's called shorting, to go short. And if we make a bet to go predicting it's going up, then we say it's long. So if I say long and short, you understand what I'm talking about. So now we've added the model predictions. Now we want to add the directional signal. And it just makes some of the calculations easier. So I'm just going to say add directional signal. And then this is the trades. So we're going to add a new column. And we're going to take the prediction. And we're going to take the sign. And by taking the sign, it's either going to be 1 or -1. And then we're going to call it directional signal. And then we're just going to check it to make sure it's been added. So if we look at the end, you can see here that if the y hat is positive, it's 1. And if the prediction is negative, it's -1. So now that we've added the directional signal, what we need to do now is to calculate the trade, the log return, if we used the model's prediction based on the directional signal. So we're going to just quickly add calculate trade log return. And we're going to specifically calculate the log return. And I'll explain later. So what we're going to do is we're going to add a new column. So we use this with columns. And it's then going to be the column closed log return. Multiplied by the directional signal. And then we're going to call this trade log return. And then we're just going to print them out. So I just want to give you like an example here. So for example, if we predict it's going up and it actually goes up, then it's a positive number, so that means we made money. I'll just show an example where we lost money. So for example, we lost money here because it predicted that it was going up. So you can see y hat's positive and the directional signal is 1, but the closed log return is negative, so it actually moved down. So you see here, this is the reason why we've got this directional signal, because it ensures that so we can calculate the trade log return. So now we know, like, if we opened and closed a trade in this time period, how much money would we make based off this model's prediction. So now that we've calculated the trade log return, so now what we need to do is to calculate what's called the cumulative trade log return. And essentially, I'll show you why we want to do this. Cumulative trade log return. So the code is going to be trades, and we're going to add a new column again. And this time we're going to, we'll do this. It's going to take the trade log return, and then there's a function to do a cumulative sum. And if you're not sure what cumulative sum and you want to get some intuition behind it, I really recommend to experiment. Just open up a toy data frame, maybe just add numbers from 1 to 10, and then call on that column cumulative sum, just to get an intuition like what it's actually doing. But it's just adding up each one from the previous ones, and it's like as a sum together. And the beauty of log returns is that you can add them up together, and this gives you the compound rate in log space. I'm not sure if I'm explaining it that well, but don't worry, because we'll see further on, it'll be more intuitive when we actually display the equity chart. So we have come trade log return, and we just want to display it just to make sure that we added it correctly. So I just want to show you what's happening here. So it's essentially like this value is this value plus that value, and this value here is the sum of this value, that value, and that value, and this continues on. It counts up all the previous values. And with log returns, the beauty of them is they have this property called time additivity, which we'll explain later, but essentially it just means that we can add them together. So that's why we have this like cumulative sum. And essentially by adding them up, we get what's called the equity curve in log space. And that's what we're going to display next. So now we're going to display the equity curve in log space. So this is essentially a visual representation of our performance of the strategy and in log space. And again, it would be incredibly boring code if I spent 10 minutes showing you how to plot it. So I've just created a function called plot column, where we pass in our trades and say what column we want to display. And we're going to say come trade log return. So this is the performance of our strategy here, based on the model's prediction. And you can see it's like quite like a linear line, but with some variance here. So one of the key things we want to look for is what's called drawdowns, and where it starts and where it ends, and if it actually goes into negative equity. So negative equity is like, let's say you start with $100, that it actually goes down to, let's say, $80. As you can see here, we never go into negative equity because it would be like a minus number. The blue line would go below this axis. But we can see, and drawdowns is when there's a drop in your equity curve. So for example, and then you want to look at, say, what's the largest drawdown. So for example, I'm just looking at this visually, then I could see like, okay, this is one of the largest drawdowns here. So this is the peak and this is the trough. And so that would probably be the worst one. And this is why we want to increase the Sharpe. When you increase the Sharpe, you're minimizing the risk. And we quantify risk as the standard deviation. So the more that we minimize the risk, the more this plot looks like a linear line. And by increasing the Sharpe, you minimize the drawdowns. And I'm going to explain later why we want to do this, because when we talk about leverage. So now that we've displayed the equity curve, now we want to discuss the second strategy decision, which is strategy. Actually, maybe move this up a bit. Decision 2 is trade sizing, because this is very important, and it's a small detail but very important. And there's two types of trade sizing that we're going to explore. One is constant trade size. So regardless of the performance of each trade, we always use the same size. So for example, we have $100 in our pocket and we want to use that, then each trade will be of $100. And then the next one is compounding trade size. So these are the two, and we're going to explore both of them and see which one increases our profits. And let's just start off by looking at the constant sizing. So I'm going to write constant sizing. So let's just imagine we're going to just start very small, that we've just only got $100. And we're going to say that the ratio of how much money that we're going to use is 1. So we're going to allocate all our $100 to this. You could experiment with this with different ratios. For example, there's this criterion called the Kelly criterion. You could use that. Personally, not a big fan of it, but just food for thought there. And then trade value is then going to be the ratio times the capital. So we're just going to use all our $100 as our initial trade value. And now what we want to do is work out our entry trade value and exit trade value. So we're going to add the columns, and the first one is that we're going to have a column that's just going to represent our entry trade value, because as I said, with constant sizing, all our trades are always the same size, so we're always going to allocate $100, and we're going to see how well this does. So even if it loses money, we're going to still bet 100. So it's using what's called leverage a little bit, but it's very nominal. So now that's our entry. Now we need to calculate the exit trade value, and we're going to do this by taking the trade value and multiplying it by our trade log return. But we need to convert it from a log return into like a simple return. We call it a simple return. So basically cancel out the log. So we then take the exponent of it, and we're just going to name this now as exit trade value. And we also need to calculate so this is the most important in terms of coding. This is the most important quantity that we want to output from the strategy, and that is the trade quantity, and this is how we would calculate it. So we take the notional value of our trade, and we take what's the opening price, because that's the price at the time of our entry trade, and they're going to call this trade quantity. And this is what is outputted from our strategy. And more specifically, we're going to look at assigned trade quantity, because with assigned trade quantity, we know, for example, if it's a negative number, we know that we're going to be making a bet going down, and by how much, what we need to send to the exchange. So with columns, trade quantity, and we're going to multiply by our directional signal, and then this is assigned trade quantity. So your strategy could pass two variables. For example, it could just pass the trade quantity and also the directional signal, but I just like to output just say one quantity, and that's just assigned. It just makes life easier. And now we just want to check to make sure that we've added them correctly. So we're going to take the trades, select. Actually, it might be easier if I just copy and paste this. Okay, and I'll just go over this. So that's at the time interval. We're going to make a trade at this price, and then at the end of the time interval, we're going to make a trade to close the position, and that's the price that we trade at. And that's essentially how much the price moves by. For our trade, that's our trade's profit or loss as a log return, and that's our model's prediction. So this is used to know if we're going to bet up or down. And always, because we're going to be using constant sizing, our entry trade value is always $100, which is our initial capital, and we're going to be using all of it. And then this is the exit trade value. So that's the entry value, and that's the exit notional value. So we make here roughly 53 cents from this first trade. And that's what our strategy is going to output and send to the exchange to say that's our order. We want to buy this quantity. So now what we need to do is to actually calculate the profit and loss of each trade, because we're just saying the return, but we're using a specific amount of money, which is this notional value of $100. So now what we're going to do is to add our trade gross P&L. And that's the trades. I'm going to add a new column as always. And we're going to take the exit value minus the entry trade value, and then this is our trade gross P&L. And now what we're going to do is I'm just going to just copy and paste. And just going to make sure that we have got this done correctly. So we then add so now we can see it more concretely. So we always trade $100, and at the end we close it, and that's the value of our trade. And you can see now that we work out how much each round trip trade, how much profit or loss it makes. So obviously if it's a positive number, that means we've made money, and if it's a negative number, it means that we've lost money. And so now what we're going to do, so this is just gross. So this means that I haven't factored in the transaction fees. And whenever you add the transaction fees, it could potentially paint a completely different picture. So even if you have a really good model, but if you add transaction fees, potentially that positive edge that you have can actually turn into a negative edge, even though you have a very good model, because the transaction fees completely changes the dynamics of your expected value. But we're going to look into that in more detail. So now what we need to do is to add transaction fees. So let's add them in. Add transaction fees. So there's two types of fees. One is called a taker, which is, remember we said, is when you're taking away liquidity, which is what we're going to be doing. And you usually pay a higher fee there because you're taking away, it's seen as like, I'm just thinking of a good analogy here. Because like the liquidity is a very scarce resource, that if you're taking away, you should pay a higher fee for it. So now we're just going to put that as a local variable, and the same for our Binance. And typically, because like, for example, if you're only trading, like if your trading time horizon is minutes, seconds, or hours, it's infeasible to, even though you may have a very good model, if you try to run it as a taking strategy, you'll probably lose money because of the fees are just too high. And typically as well with an exchange, the more you trade, the more your fees get lowered. So for example, if you're making lots and lots and you have huge volume, you pay less. So you can lower your fees if you increase your trading volume. So now this is the maker fee, and now we're just going to add them in. So trades with columns, again we're going to add the columns. The first column is going to be to add the taker fee, and to take the taker fee we need to calculate the round trip transaction fee. So we need to calculate the notional value at the entry and at the exit. So what we do here is take the entry trade value and then multiply it by the taker fee. And we do exactly the same, but for the exit trade value. So for example, if we started with 100 and we made, for example, 105, then we need to pay the transaction fee on the 105 as well. So this is why we broke it up into entry trade value and exit trade value. And then we need to multiply that by the taker fee. And then we're going to call this the taker fee. And we're going to do exactly the same. And ideally it would be nice to, because this code is very repetitive, that we wrap this as a function. But because this is just an introductory video that I won't do that. So entry trade value multiplied by the maker fee plus the exit trade value multiplied by the maker fee. And what we're going to do is also just compare, for example, if we see how the taker fees impacts our equity curve, like the performance, like see how much it absorbs into our profits. So we're going to look at the equity curve for gross profits, but then we're also going to look for net, specifically if we ran it as a taker strategy and also as a maker strategy. We're going to see something quite interesting. So this is the maker fee, and we're going to display it. And I don't want to type out all the columns, so I'm just going to copy and paste them. Okay, so here's the fees. So you see the taker fee, and I just wanted, this is a much better time to explain the impact of transaction fees on our performance. Because for example, actually no, we'll do that when we calculate the net fees, but just going to give a quick teaser. So for example, look, if our loss is 52 and our transaction fee, let's say here is 5, it's going to increase our loss. And let's just say, for example here, it's 13 cents and nearly just half of it will be absorbed by the taker fee. So this is why it has a negative effect on our expected value, because it decreases our profits and also magnifies our losses. And for example, if we had a profit and it was just only 2 cents, so even though we predicted correctly, but because of the fees, we actually lost money. So this is why it is extremely important that we calculate the net P&L. Whenever this is a very imperative, because even if you have an edge, but if you don't model the fees, this is like poor execution. So now that we've added transaction fees, now we're gonna calculate the net P&L. So now we're going to calculate the net P&L. And this is, we're going to add a column again. And we're going to take gross P&L against the maker fee, and we're going to call this the trade net maker fee. Oh, sorry, maker P&L. And we're going to do exactly the same. I'll just copy and paste this. And I feel uncomfortable copy and pasting because this is really bad coding practice. It would be like, if you see this sort of repetition, it's better to create a function, but just I don't want to increase the length of the video, so I'm just going to cheat here. But it's, and I think I even created a function in this in research, which you will see later on. And so now we're also going to just take these parameters here. So we'll run this now. So now we see the impact here, so more concretely. So for example, this lost 52 cents. And because the taker fees, it actually increases the loss now. So it's rather than 52, it's 58. And for example, here we made 53 cents, but it's decreased our profits. So it's just 47 cents. And you can see here, like it's, because we only just made 13 cents on this, that nearly like 50% of it has been absorbed by the transaction fee. So we only just make 7 cents. So imagine if we just like only made like 4 or 5 cents, then it would actually be, even though we made a profit, but then factoring in the transaction fee, it's actually we've lost money. So that should be a bit more intuitive now. So now let's display the equity curve for this. Because we just showed the equity curve in log space, we haven't actually seen it like with a concrete trade sizing. So now what we're going to do is to display equity curve, or equity curves for constant sizing. And I just want to show the impact of transaction fees on our equity curve, because you'll see that it magnifies our drawdowns as well. So now display equity curves. So I have a function to do this. Actually, it's inside my research module, but I'll just code it here. So you have the capital, the column name, and the suffix. And suffix is just the text that you want to add at the end. And then we just return the capital plus col name. And then we're going to calculate the cumulative sum, which we should know by the previously. And now what we want to do is we want to create the alias. I actually want to put that here. And then the alias is going to be equity curve suffix. So now trades equals trades, and we're going to add the new column. So we're going to call equity curve, going to pass in the capital, and oops, going to call the column that we want to display, which is trade net taker, or aggregate based on taker P&L taker. And we're going to do exactly the same. But for trade net maker P&L. Equity curve, capital, trade, gross And now I'm just going to just make sure that they're being displayed correctly. So now I'm just going to run this. So now this is the equity curve as a time series. So now we're going to display them all individually. So I'll probably just maybe easier if I just copy and paste this. So now we're just going to have a look at the equity curve in P&L space and gross. Oh no, sorry, this is the taker. So I want to show, like for example, originally if you saw the gross in that it never went into negative equity, and I just want to show that the impact of the taker fees has on our performance. So it has a very similar. The curve looks very similar to the gross return version, but you can see now that it actually goes into negative equity at some time point, but not for too long, and it jumps back up. So this you can see visually the impact of how the transaction fees absorbs into our profits and magnifies our losses. So and also our drawdowns will have increased as well. So but you see, because we still have a positive edge, statistical edge, that we make money, but it just means that it just increases the variance of our returns. So now that's the taker. I want to show the maker, because it looks very close to another important detail here. So look, I think it just makes just below $115. And I just want to show, like, if we ran this as a making strategy, so my personal preference would be to make it a maker strategy out of this, because we don't go into negative equity and the drawdown is not as large and we make more money. But the reason that we're not running a maker strategy is because this is like an introduction series, and running a making has a more complexity. So maybe in a future video series I may create like let's build a market making strategy. But just for this video, this series, we're just going to be focused on taker. But if I was going to use this in production, then I would create a making strategy out of this. So and you can see here that we never go into negative equity and we make more money. So it goes over 120. So it makes sense that we run this as like a making strategy rather than a taking, because the fees don't absorb so much into our profits. And I just want to show you, now I want to just calculate the total net. So what we're going to do now is this. Calculate total net return using constant sizing. And to do this, we're going to create this as a local variable, because once we've defined it and store it, we're going to compare it with compounding trade sizing. So trade sizing net return equals, and we're going to look at the trades, we're going to specifically look at the equity curve taker. We're going to take the last known value, and we're going to then divide it by the capital, and then -1. And then we're just going to display it as well. So this is like 14.4% using constant sizing. So now what we're going to do is we're going to now experiment with compounding trade sizes and compare this to constant sizing. And I'm going to explain what is compounding trade sizing, because this it sounds complicated, but it really is not. So let's start with an example. So for example, if I start with a trade that trades 100 and I make $2, so then the exit value is 102, then I've made 100 plus 2, and compound is essentially reinvesting the money. So for example, now my entry trade value for the next time interval will now be $102, and let's say I make $3. So now I've made $105, and that's essentially 100 plus 2 plus 3. And now let's just say now I have a notional value, my trader has a notional value of $105, and let's say I lose $1. So now my exit value is now 104, and that is 100 plus 2 plus 3 minus 1. So this is like we're compounding because we're reinvesting the money, and this is why we're using log returns, because we're modeling, log returns model the compounding, and to model the compounding return is you simply just have to add the log returns up together because of this beautiful property called time additivity. So I'm just going to give you a bit more of a concrete example. So maybe if I just copy and paste this in, this would be quicker. So let's just say that we have a log return of this value, positive, and this is like our trade log return, and we take the exponent to give us the normal simple return. So that's our first profit. So we've made 54 cents. Now, so for the next time period, we take that profit. So the P&L will take that and then multiply that by our next trade log return. And you can see that we're making more money. And now let's just use on the third trade, that we take the P&L from the second trade and we reinvest it for the third trade, and this is the trade performance. So that's our total return. However, so for example, then essentially what it's doing is just, we're just going to do this in one line, which it's doing this. So actually, I'm just make sure that's the log return one. But there's going to be some floating point precision error. So let me just. Oh, let me just. I don't even need the parentheses. Okay, so that's better. So, and I just want to show this time additivity because I've mentioned it a few times, but I just want to show it a bit more concrete. So time additivity. Oops, I spelled that wrong. And so essentially with the time additivity is that if we take our capital, we just multiply it by, we can just sum them together. So we can just do log return plus log return 2 plus log return 3. And we're going to get exactly the same answer. So we're just adding them up. So this is how it can model compounding. So this is one of the really nice properties of using log returns. So I'm just trying to emphasize that it's just not purely just an academic exercise. There's actually lots of practical benefits of using log returns. So now what we're going to do is to add the compounding trade sizing to our trade data frame. So add compounding trade sizes. trades with columns. And so the first column is going to be come trade log return. And we're going to take the exponent of that. So essentially taking it from log space into a simple return. And we're going to multiply that by the capital. And that's going to tell us the entry trade value size. And what we need to do though is to shift it. I'll explain, we'll look later I'll show you what it's actually doing. So don't worry if you don't understand what's going on. And we're going to fill null, because when you shift a column, that the first row will always be, there'll be a null. And we need to fill this up to say the initial capital that we're starting with. So that's the capital here. And then we're just going to alias it and call it entry trade value. Because we're essentially modeling that we're compounding the trade size, and you can see rather than be static, it'll be a constantly changing number. So now that we've done that, now we're going to do the come trade log return. We're going to again take the exponent and multiply it by the capital, but we're not going to shift it. And then this is our exit trade value. And I had a question like, why are you chaining up all these with columns and not put them all together in one with columns? And that was a really good question. So I just want to explain it here. The reason is because, for example, I can't reference X trade value in the same argument. So because it hasn't created it yet. So that's why I have to chain them up, because then I can reference it later on. I could just use the full form like this, but then I just think for readability, it's much better if I just, even though it's you're chaining these together, it just adds more readability to show you how you're actually defining them. So now what we want to do is take the column trade value and divide it by open, and we're going to multiply it by the directional signal. Oops. Alias, and this is our signed trade quantity. And also we're going to calculate the trade gross P&L. So to do this, we know how to do this, which is the exit trade value minus the entry trade value and this is our trade gross P&L. And then I'm just going to copy and paste the select columns. And the reason I'm just selecting, not selecting all, because it turns into a huge, a lot of columns, so it just cleans up the columns that we're not interested in. So now you can see here, the really important observation here is that our entry trade value, and I'm just going to get a drink. So we can see here that our entry trade value is not constant now. You can see that which is good, because you can see here that it's increasing. So for example, our very last trade, our trade value is 128. So you can see that we've made just over $28, and we're reinvesting that in. Because we've got the edge as well. So now what we want to check is like, what does this have on the impact on our profits? And remember, our key idea for the strategy is to increase profits from our model's edge. So let's see the effect of compounding on the performance. Okay. So now what we've added the trade sizes. So now we just need to do some of the add the transaction fees. And because it's I showed you, I don't want to repeat that code because it's just boilerplate code. So what I'm going to do is I have a function to do it, and so it's just a nice one-liner. So then we pass in our Binance make a fee and Binance take a fee. Trades dot select date time entry trade value exit trade value, and we also want to select the transaction fee maker and transaction fee taker. So we see the fees. So now that we've added the transaction fees, I'll just make it more clear what we're doing here. So add transaction fees. So now what we're going to do is to add the trade net P&L. So again, I could probably create a function to do this. So we're going to take the trade gross P&L and then minus the transaction fees. And we're just because I'm just going to do it for the taker because we're not interested. We're not running a maker strategy. So fee taker. And the alias is trade net. That's essentially the name of the column. That's our column name. And I'm just going to, pardon me, is to copy and paste the columns. Okay, so now we see the gross and also the net with respect to the taker fees. So, and again, it eats into our profit and it also magnifies our losses, but not by a huge amount. So now let's look at the equity curve for this. So we will scroll down. Display the equity curve, compounding. Research dot add equity curve, trades, capital, trade net taker P&L. Plot, we're going to just use static time series, trade, pass the symbol, and this is the column that we want to display, so equity curve taker, and then the time interval. So again, you see because of the taker, but it doesn't look too much difference here, and I think we just make a bit more money than if we were just using a static constant size, but we can just check this by calculating the total net return. And then what we'll do is so now we've got the compounding, so now we can just compare. We're going to calculate the total net return now for compounding, and then we're going to compare it with constant sizing and see, make a decision which one we're going to use. And purely it was just going by numbers, so whichever gives us the best total net return we're going to use. So calculate total net return for compounding trade sizing. Total net return, trades, equity curve, taker, -1, capital -1, and then I'm just going to display. So if I recall correctly, it was about 14.4% the previous one. So you can see here this is 15.2%. So we're going to use compounding. And we're going to see later on how when we use leverage and compounding that you're going to get some phenomenal returns with the combination of these two. So we want to use compounding, and I just want to show you again, I think the constant sizing net return is 14.4. So if we let me just show the difference. So round compound total net return minus the constant sizing. I'm just going to round it to 2 decimal points. So yeah, just an increase of 1%, but you know, we're not using any extra capital, so it makes worthwhile to use the compounding, especially when we're going to be using leverage, and it really it's going to magnify things. So, and that now I've just been talking about leverage, so that's the next key decision. So strategy decision number 3, leverage. Okay, so essentially leverage is borrowing money, and the idea of the borrowing money is to increase our profits or increase our rate of return on initial capital. And so for example, we could, so you'll see things like on exchanges, like how much leverage you can use, and it can be up to like 20x or 50x, which is an insane amount of leverage, and I don't recommend that level. But I just want to show you, for example, so if I was leveraging 4x, then my trade, essentially my trade size would now then be, rather than just be $100, let's just say I've only got $100 to my name. And you know, I'm going to increase my trade size by 4x. So now our trade size, initial trade size, is going to be $400. So in theory, we're multiplying our trade size to increase the returns. But what's very important is that we're not multiplying the actual trade return. So this is a key mistake I've seen, where some people actually just multiplying the trade's log return, and that's not what we're doing here. We're leveraging the trade size. So, and just remember that it amplifies both your profits and losses. So it's really important that you have a positive expected value, and you've minimized risk as much as possible and quantified. So for example, you have a very high Sharpe ratio because you have minimal drawdowns. And leverage only works when you have a high Sharpe model. The more risk you reduce, the more drawdowns you reduce, and the more leverage you can use. So now the key decision is like, should we use leverage? And if so, how much? And what's the sweet spot? But you've got to be very careful with leverage, because it's not a golden utopia where you can just like use it and straight away you're going to increase your profits by an insane amount, because it can easily wipe you out if you have too much leverage and you haven't modeled risk correctly, because it can just a small price movement against you can wipe you out. So this is what, for example, you see these what's called margin calls, where you have to add more money to maintain the margin. So now what would, because I don't want to go all over that code to calculate the quantity, the gross P&L, I have a function that does it for us. So I'm now just going to call it, so it's add compounding trades, capital, leverage, so what our maker fee is and what our taker fee is. And then I'm just going to display the trades. So this, so let me just, because you're going, if we see the notional value at the entry and exit, it will make sense. So we said that leverage is 4x. So if we have a look at the entry trade value now, you see that we've only got $100 to our name, which is a very humble amount, but let's say we're leveraging 4x, and this is like essentially our trade size is 400, and it's essentially like now the extra trade value is 402. So if we look at the gross profit, so instead of, if I recall correctly, it was 53 cents as the first trade, but now our gross P&L is $2.14. So it's magnified our profits. But again, as I said, not only does it magnify your profits, it can also magnify your losses. This is why it's imperative to have a positive expected value and with like low standard deviation of returns. So, and like for example here, this is magnified our losses, like here, that's quite a big one. So this is why I really focus on having a strong positive expected value and a high Sharpe value. So now that we can actually see our equity curves here, both as a maker and a taker. So I want to now, just to show you what the total return is. So now what we're going to do is calculate total net return and see what the impact it has. Okay, oops, mark down. So again, to calculate it, we take the trades and we're interested in the equity curve, but for taker, and I'm just going to do -1 divided by the capital. So that's our initial capital, which is 100, not 400, because that's actually what our account balance is. -1. Oops, I should change that back to Python. And I need to close the string. So you see, with using a mixture of leverage and compounding, our return is now 61%. You may be thinking, okay, what about using like 8x leverage? So now let's look at, like, if we increase the leverage now. So let's ask the question, what if we increase to 8x leverage? And I think in the US, this is like the legal limit of how much leverage you can use. So for example, let's trades, research, add compounding trades. Again, it would be, I don't want to be copy and pasting code because I just did it once just to show you the calculations. So again, I reduced my boilerplate by reusing my function. So I'm passing the trades, I say what a capital is, which is 100, but this time I'm going to say the leverage is 8x, and we're going to pass in our maker fee and also our taker fee. And now I'm just going to maybe calculate the trades, equity curve, taker. And again, we want the last value, which is then divided by the capital -1. So you see here, this is like 122%, which is an insane amount. But potentially, the more leverage we use, the more risk of drawdown. Sorry, not drawdown, is risk of liquidation. So if the price, the more we increase it, but we're going to see this later because I don't want to paint it that, you know, just there's a huge risk to using leverage. You got to study price movements very accurately to understand what's the sweet spot of leverage. And even if you have the sweet spot, there could be like an outlier where you get what's called like a fat tail, where it has like an extreme price movement, which is unheard of. So you need to factor for extreme price movements. So I only recommend to use a small amount, even like if you're your first time running an algorithm to do trading. I don't use any leverage, so set this to 1. So you're not using any leverage. But then once you get more experience and you can adapt, maybe you can create an algorithm that actually adapts the leverage. So like Bayesian statistics, whatever, to just adapt to the performance. Anyway, so now we can see that if we use it, we get insane returns. And you may just be thinking, okay, have I manipulated anything here? Like, okay, is my model like, because the model is still only winning like 56% of the time. Your intuition may be saying that, okay, for those insane amounts, you've got to be winning like 199% of the time, but you really don't. And I just want to empirically verify with you. So let me just add a new column. So win rate hasn't changed. So it's actually quite low win rates. So I just want to show you. So if I do trade select, and I'm going to select the trade log return. And we're only interested, we're going to set it like, if it's positive, then it's true. And then if it's negative, then it's going to be false. If we take a mean of a Boolean column, then it's going to give us the win rate. So if we calculate this here, so it only wins 56% of the trades, and you can see. So you may be I'm not sure why it has, like, for example, we're using like 61% when it was 15% without leverage. So it's like an insane increase in the returns. And the key reason is because we have a model with a statistical edge, a positive expected value, very high Sharpe ratio, but also it's the mixture of compounding and leverage. So these three components together can give you phenomenal returns. So hopefully you understand and another key lesson here is that you shouldn't focus purely on the win rate. It's unrealistic that you win all your trades. You want to just have a positive edge, make as many trades as possible, and make sure that you compound and you use leverage correctly. I could even just have like a 2-hour video just purely on discussing leverage. But maybe that's another future series. But what I want to do is to model liquidation. So at the moment we're not doing any modeling of liquidation, and I'm just going to do like a very primitive modeling of liquidation. So we're going to factor in liquidation. And this is essentially when the price moves against us and when we essentially get all our positions closed, and we'll end up with like zero money. Balance either zero, or the exchange or the broker will ask you for money. Anyway, so we're going to factor liquidation, and there's many different ways. So as I was saying, like, liquidation is a double-edged sword. It can amplify profits, but if you just use too much, just a little bit too much, it can just wipe all your money out. And you could, even though if you've got like a really good model, but this is why the model is important, but your execution is equally as important as your model's edge. And essentially, your equity is what's called a maintenance margin. You've got to have a certain amount of money to keep the position open, and the calculation differs from different exchanges, but it's roughly similar, the same calculation. So I just want to show you, for example, I'm just going to maintenance margin. So typically the maintenance margin is like oops, let me just convert this to Python. Liquidation price. Actually, I'm just actually going to copy and paste because it's, and then explain the code. So the calculation is a bit different if we have a long position. Remember, long is like we're making a bet that the price is going to go up, and then a short is essentially we're making a bet that the price is going to drop down. So the calculation is different for long and short respectively. And I'm just going to run this. So now I just want to show how liquidation affects your long position with respect to the amount of leverage you use. Pardon me. So show how leverage affects long positions. Okay, so maybe I'll just copy and paste the code in. So let's say the current trading price is $200 and we're using 2x leverage, and the requirement is that they have a maintenance margin of this value. So this tells us that would only be liquidated when our price, like our whole position, is closed when the price gets to this level. So, for example, nearly like just below 50% is when it gets liquidated. So, but I'm going to show you now, like as we increase the leverage, the higher this number is, and the more chance of the probability of being liquidated is. So, for example, now if I say this is 4, so now the price is now jumped up. Now it's just under around $40. That it needs to drop down by for it to liquidate. So maybe just before that price, you have to add money in, so like a margin call, implicitly or explicitly, to ensure that you don't get liquidated. And so now I want to show you with now with 10. And leverage. So with 10 leverage, like the price, again, it's getting closer to 200 now. So this is why, this is really the key difference between investing and gambling, is because you have an edge, and also a statistical edge, and it's also how you execute that edge. Whereas, like, for example, gambling in a casino, the odds are against you. So even if this is where, for example, like you have card counting, so you haven't sort of like an edge to beat the casino. But if you use too much leverage, and for example, if you're just like a first-time trader and you're really ambitious and you put a very aggressive trade and you like 20x leverage, and it could be a good trade, but just it's so sensitive to a price movement that it can wipe you out. So this is like probably a very common, especially in crypto, like especially with Trump's announcements on tariffs. There was huge amounts of liquidations that happened because and this is why it's so important to model price movements. And maybe that's another video for the future. So, and I just want to show like the insane amount, like for example, I think there's even been like 50x, but just show you 20x. So with 20x, like it only just has to move down just under $10 for it to be liquidated. So this is extremely risky. So this is why it has to be like a sweet spot of just the right amount of leverage where we don't have the risk of ruin. So, and I just want to show the opposite side now. So for example, how it affects shorts positions. So show how leverage affects short positions. just going to copy and paste some code. Okay, so and now it's the opposite way around. So for example, a short position is we're making a bet that the price is going down. So if the price moves against us, then that means the price is going up. So for example, for us to be liquidated using 2x, our liquidation price is 396. So it has to move up by this amount or equal to, greater than equal to, for it to be liquidated. And again, I'll just quickly go over it because it's just the same concept. Now if it's 4x, it's closer to 200. And then if I just say like 10x, and I also just want to show like 50x, I think there are some crypto exchanges that do 50x, and just show like how insane that, like, so if it goes above 203 and this price, then it's going to be liquidated. So yes, so just be very careful with leverage. So now what we want to do is to add liquidation prices to our data frame. And I just want to show you what our current leverage is. And the leverage show you here is 4. And now what we're going to do is to add a new column, and the new column is essentially going to calculate the liquidation price. So to do this, we need to add a new column, and just as always, we use our trusted with columns. And now this verbiage we've not used before, so we're going to use when. So when the directional signal equals 1, so this represents a long position, then we're going to do the following. We're going to maybe scroll a bit here so we can see. I'm going to take the open price, because that's the price that we at our entry value, and multiply it by the leverage. So essentially that formula that I showed you previously, we're going to just calculate it, but this is what's called like a factorized version, because we're rather than just be a scalar value, a single value, we're working with an array. But you don't need to know the full. Don't worry if you don't understand what factorized means. It's not that important. Leverage plus 1 minus maintenance margin times leverage. And so that's our liquidation price for a long. And now we're going to do exactly the same, but for short position. So when the directional signal equals -1, then we're going to calculate the liquidation price for a short position. So, and again, we want to use the open price multiplied by the leverage divided by leverage -1 plus maintenance margin times leverage. Then otherwise none, but there will be no, it's either, our signal is either 1 or -1. And then we're just going to call this column liquidation price. And now I'll just copy and paste. Now I'm just going to just make sure that it's just to show you. Okay, so we see our open, high, low and close. So within this time period, that's the highest price it goes up to, and then this is the lowest price that it gets to in this time interval. And this is our liquidation price with respect to the leverage that we're using, which is 4x. So we buy at this price, we go long at this price, but if the price moves against us, more specifically goes down by this amount, then we get liquidated. So now we know what the liquidation price is. Now essentially we just either, if it's the directional signals 1, we want to make sure that it doesn't go over this liquidation, if it's a long position, if it's 1, then we need to make sure that that we need to check this with respect to the low price. But let's do the calculation. So now what we need to do is, so we need to add the liquidation flag. So this should make more sense now. So essentially the flag is just going to tell us if it's liquidated, if it does liquidate our position, false if it doesn't. So then what we then do is then filter out. But yeah, anyway, let's just code it up. Trades with column, because we add new columns as always. Then what we want to do is calculate the worst price based on direction, and then that's when the directional signal equals 1. Then the column is low. Otherwise, the column is high. So basically, we're choosing for our comparison either the high or low price depending on the directional signal. And then we're just going to call this worst price. Okay, so now that's our first column that we're going to add. Now we're going to add the liquidation flag. So this is and we'll just put this on the next line. The directional signal equals 1. And when the low price is greater or equal to the liquidation price. Then if this predicate is true, then we want to set it to true. But when we have a look at this, and then if the column directional signal is -1 and the column high is greater than or equal to the liquidation price, then that's also true. And otherwise, it's false. And we're going to name this column liquidated. and then we're just going to okay, I just need to sort this out. So I think why is this actually what I might just do is just copy, so I just rather than to fix the syntax issue, I'm just going to copy and paste. There we go. So now we see the liquidation price, and we've got a flag now to see if it's liquidated or not. So the lowest price never goes down to this price, so yeah, it's not liquidated, but we don't want to manually check each individual row, so we want to do this automatically. So that's the next thing to do now, is to find any liquidated trades. And when there's a liquidated trade, then this means that our position is closed and then we lose money. So let's do this now. So, oops, we need to do the markdown. Then we take the trades. I'm going to filter them where the column liquidated equals true. And this should be 0 if there's no. So this tells us that by using 4x leverage that we don't have any liquidated positions at any time. So we can safely use this. Now I say safely because we still need to do a more comprehensive analysis of the price movements, but from our running this against the historical data, that we can see that we can safely use 4x leverage. That's roughly about 60% rate of return. And again, this is a mixture of the model's edge, compounding, and leverage. So these three combinations. So, and really this is now the second part finished. The third part is actually where all the implementation. So this is still like, we're actually going to write the code to build this up, and we're going to we're going to put this live into action, where I'm going to put some, again, I'm just going to use small amount of money because just to show like how you can practice and experiment with just a small amount of money. And some of the topics we haven't covered, because this is just a foundation to build upon. So for example, we have not done, I haven't talked about alpha decay, which in machine learning is known as model drift. And this is where the prediction performance starts to decrease. And like, how do you manage this? So we haven't discussed this. Another important issue is market impact. So I specifically chose a very tiny trading size because if we were like trading in very large sizes, we would need to model market impact. And this is essentially, if we have place a big order, this could potentially move markets against us. And again, just by using a very small amount, we don't have to model this. There's another fee that we haven't discussed, which is funding fees. So either when you hold a position, you have to pay a fee, or you could actually receive money for holding that position. We haven't factored this in. And another variable is slippage, which is when we have a large order, we may not always get the best price. So for example, if we place a large order, we may get what's called slippage, where we get the prices below the top of the order book. So let's say the best bid is 100, or best item we buy is 100, but we may not always get at 100, we may get at 101, 102. So this is called slippage. So anyway, it was really good fun to make this video. Please like and subscribe, as this is my feedback signal to know if you want a final video in this series. Feel free to leave a comment down below. Your feedback is very important, and I love reading the comments. And yeah, over and out.